In this demonstration, we will take a look at a NerveCenter basic device monitoring model and explain how, even at the most fundamental monitoring level, we approach network monitoring in a more thorough way. All management systems do some form of basic device monitoring, typically a simple up-down status check. Most other management platforms verify up-down status through a simple connectivity test using ICMP pings to send out an echo request and listening for an echo reply. Consider this scenario. Is there a set of network conditions where I could send an echo request and not get a reply, but the device I'm trying to reach is actually functioning properly? The answer is yes. The device could have a router in front of it that is the real problem, causing the pings not to get there. You are getting a false negative. Testing connectivity is obviously an important part of monitoring a device, but we will show it should not be your only criteria. Now we're going to show you how NerveCenter out of the box handles the same type of basic monitoring scenario. This is a visualization of the finite state engine, the logic engine that powers NerveCenter. All of NerveCenter's functionality is created through finite state models. In all NerveCenter models, we start at the ground state. Ground state is a condition in which we either haven't begun polling the network or we've been polling and everything appears to be operating properly. Starting in the ground state, we create polls to learn more about the condition of the network or the status of the specific devices. In this model, we have a looping poll set to check the status of the SNMP agent on the device. If we can get a full response from the device using SNMP, we've learned that the device has connectivity and its operating system is functioning properly. In our model, we will return to the ground state. We are not just testing for an echo reply, we are making sure the operating system is working. It is entirely possible to have a condition where you could ping a device and get a response, but the device's operating system is locked up and non-functional. In most devices, ping responses come from a NIC card. The NIC card has its own code loaded onto it, enabling queries even if other software on the device isn't working properly. As a result, you can get a false positive. The management platform is telling you the device is up, when in reality it could be completely unusable. Continuing with our NerveCenter model, if for some reason we cannot reach the SNMP agent or it's otherwise unresponsive, we declare an SNMP timeout. We move to the error state and start polling more frequently. This is an example of NerveCenter's smart polling, only polling the network when it is actually necessary. The model now tests the agent again with a faster poll. If we can reach the device this time and it responds properly, we can assume that there was some network hiccup that prevented the response before. We move back to the ground state and start over. If, however, we can't get a response from the SNMP agent, we move to the unknown state. In the unknown state, we don't know why the agent isn't responding. At this point, we take a step back from SNMP. Within a single model, we can test a device using multiple protocols. Here, we'll switch to an ICMP ping. If we get a ping response, we know that the device itself is responsive, but the SNMP agent is likely down. We can't determine what level of alert to send the operator at this point. Now let's assume a scenario where we are getting an ICMP response, but it is not a reply directly from the device. This message tells us that the device is unreachable. If you are making an echo request to a device that is 2 or 3 hops away, you might get an ICMP response from an intermediate hop, likely a router of some kind, saying that the router was the last step in the network chain reached, but the device could not be reached. Would you want to declare the device down at this point? Not necessarily. In NerveCenter's case, we're looking intelligently at the ICMP responses, and we determine that the device is simply unreachable, moving to the unreachable state. Once we have reached the unreachable state, we might want to check other parts of the network. We could send triggers to other models that will run other tests in the network. We could send out a low-level inform to let the operator know that the device is unreachable. But here we are going to continue our test strictly looking for a device down. Now, if we get an actual ICMP timeout directly to the device, if it looks like all routing is properly in place, the device should be responding but isn't, then we declare that the device is down. At this point, we've tested all of these conditions and none other conditions apply, so we conclude that the device is actually down. As you can see, we've taken simple up-down monitoring to a greater depth by checking a wider variety of conditions and using more of the protocols at our disposal. The model may look pretty complicated at first glance, but once you walk through it, you see that it really isn't anything more than a series of conditional tests. This model demonstrates some of the concepts and capabilities of NerveCenter. We don't have to take a single test or query and use that as our sole mechanism for making a determination. We can chain things together, remember where we were, and make decisions along the path. We have shown how you can use NerveCenter out of the box to enhance basic device monitoring, reduce event storms and false positives, and improve IT efficiency.